This podcast is on colligative properties. Colligative properties are those that depend upon the concentration of the particles in a solution and not upon the identity of those particles. Some examples are freezing point depression and boiling point elevation, which we will do in Chem 1, and osmotic pressure, but more about that possibly next year in AP Chem. For the freezing point depression and boiling point elevation calculations, however, we need a specific concentration value known as molality. Not molarity, but molality. And this is the moles of the solute divided by the mass of the solvent, measured in kilograms. We end up with units of moles per kilogram, and we give it the symbol of a script lowercase m. So, what is the molality of an antifreeze solution containing 645 grams of ethylene glycol in 3.6 liters of water? In order to calculate the molality, just like molarity, you need the moles of the ethylene glycol, which is 5.536. And then you go ahead and calculate the molality, remembering, of course, that the density of water is 1 kilogram per liter. The molality, it turns out, is 1.538. And we report that as 1.538 molal. Freezing point depression. Each mole of solute particles lowers the freezing point of 1 kilogram of water by 1.86 degrees Celsius. That we call the freezing point depression constant. And we're going to use it, along with molality, to calculate freezing point depression with the equation change in freezing point equals the constant times the molality. So, what is the freezing point of that antifreeze solution that we calculated earlier? We know that the molality of the solution is 1.538 molal, and we know the freezing point depression constant, so this is a simple matter of multiplying them together. We end up with the change in freezing point being 2.86 degrees, and so to get the final freezing point, you need to take the initial freezing point, subtract from it the change, and get negative 2.86 degrees as your new freezing point. Well, the other colligative property was boiling point elevation. Each mole of the non-volatile solute raises the boiling point of a kilogram of water by 0.51 degrees. K sub B is 0.51 degrees C over molality. The calculation of boiling point elevation is the same as the freezing point one, except the constant, of course, is different. So, what would that antifreeze solution boil at? Again, we have the following data. We know the boiling point elevation constant, and we can do the calculation and get a change of 0.784 degrees. And so then we know that the water solution will now boil at 100.78 degrees. Those calculations were for molecular, non-volatile, non-electrolytic solutions. As you know, electrolytes or ionic compounds dissociate into ions when they form a solution, and since colligative properties are properties that depend only on the number of solute particles and not their identity, we have to make an adjustment when electrolyte dissolves. Sodium chloride, you see, dissociates into cations and anions. You're well aware of that. So in a 0.1 molar solution of sodium chloride, we have 0.1 molal sodium and 0.1 molal chloride. And so that means that we have 0.2 molal ions in solution. Now, we have, therefore, a new factor in the equation, and it's called the Van 't Hoff factor. It's the actual number of particles in solution after dissociation divided by the number of formula units initially in the solution. So, for example, in non-electrolytes, the I is 1 because they dissolve completely. But for something like sodium chloride, the I, or Van 't Hoff factor, should be 2. For calcium chloride, it should be 3. What we have is a modification of the change in freezing point calculation where we introduce the I, or the Van 't Hoff factor, into the equation. As you can see, it's named after Van 't Hoff, whose picture is in the lower left. Boiling point elevation is the same thing. And so now we need to know something about the electrolyte if we're going to do the calculation. So if, for example, what is the freezing point of a solution prepared containing 345 grams of calcium chloride in that 3.6 liters of water? The calculation is very similar, and I'm not going to walk through it. You calculate the number of moles of calcium chloride, calculate the molality. Since one calcium chloride produces 3 ions, the Van Hoff factor is 3. Delta TF is equal to 3 times the 1.86 degrees C per mol times the molality equals 4.82 degrees C. And that means that the freezing point is lowered 4.82 degrees C. Well, it turns out that colligative properties are at the core of some relatively common activities. The melting of ice on the roads in the winter is a result of the colligative property of freezing point depression. We also use that to lower the temperature of a brine solution if we want to make ice cream. So, let's calculate the mass of sodium chloride needed to produce 1.5 liters of a brine solution, which would have a freezing point of -10. In a sense, we're going backwards. We know that delta T freezing is -10, that I is 2, and that the Kf for water is 1.86. If we rearrange the Van Hoff factor included delta TF equation, we get that the molality is equal to delta TF over I times the Kf, and in this case the molality of solution required would be 2.866 molar. You then work that thing backwards and discover that we need about 4 moles of sodium chloride, or 235.6 grams. This calculation is fairly common. The other unknown, of course, could be the molar mass of the material, and indeed the molar masses of large proteins is determined using freezing point depression.